90% of students sitting their Cambridge IGCSE physics paper lose completely avoidable marks because of one specific resultant force conclusion. Let's jump straight into the data and see exactly why this happens, and more importantly, how you can make sure it never happens to you.
Take a close look at this statement. The object accelerates because the forces are 10n and 5n. Now, is this correct? If you wrote something like this in your last mock exam, you've just walked right into a classic trap. This common, flawed answer absolutely destroys grade boundaries because it lacks specific scientific reasoning and exam-safe wording. It completely fails to calculate the net resultant force, it doesn't mention the direction, and it totally ignores Newton's second law of motion. Examiners see an answer like this, and they instantly bring out the red pen. You know, it's surprisingly easy to lose marks on your practical and data analysis skills. You see, ordinary revision, like just memorizing your textbook or highlighting a bunch of equations, often falls completely short when you're actually sitting there staring at the exam paper. If you aren't thinking exactly like a Cambridge examiner when you're handling experimental data and practical investigations, all that textbook knowledge just isn't going to translate into points. You really need a structured system. Section 1. The Data Detective Framework. How to build top-band answers. Let's get right into it. This right here is the unbreakable chain that guarantees you a perfectly structured answer every single time. Step 1 is your concept. Ask yourself, what is the fundamental physics principle at play? Step 2 is evidence and data. What specific numbers or anomalies are staring right at you from the source table or graph? Step 3 is scientific reasoning. How do that data and your concept actually link together? And finally, step 4 is examiner wording. Are you using the precise terminology the mark scheme actually demands? If you stick to these 4 exact steps, your answers become absolutely bulletproof. So let's apply this framework right now to get you a quick win. We'll start with a straightforward setup: density. Step 1 of our framework tells us to establish the concept, which is mass per unit volume, or m divided by v. Super simple, right? But just knowing the equation isn't going to get you the highest possible score. Because pointing out the equation is the easy part. The real trap is in how you handle the experimental data itself. Take a really close look at the data for Block A, Block B, and Block C. Just reading the facts isn't enough. You have to put your data detective hat on here. There are critical errors hiding right in plain sight. Now, in just a moment, I'm going to show you the one graph axis mistake examiners absolutely love to penalize. But first, you need to use the framework to spot the critical errors hiding in this very table. Because if you can't spot them right now during practice, they're going to be virtually impossible to catch under the pressure of the ticking exam clock. All right, so the crucial issue is right here. Look at Block B's density calculation, 2.1818. The student rounded incorrectly and completely abandoned consistent significant figures. In Cambridge physics, premature rounding or just spewing out 4 decimal places when your raw data only has 2 significant figures will instantly cost you the final accuracy mark. Your calculated density needs to align perfectly with the precision of your mass and volume instruments. No exceptions. Section 2, Investigating Pressure. Spot the anomalies. It's time to test this out on a slightly harder concept, where data anomalies are notorious for hiding in plain sight. I challenge you to act as the data detective right now. Look at this pressure experiment measuring force against area. Go ahead and pause for a second if you need to. Try to spot the glaring anomalies and the inconsistent decimal places. I promise you, they are in there. Can you see exactly where the student went off the rails? Okay, here comes the examiner's red pen checklist. Did you catch it? Trial 2 lists the pressure as just 50, completely dropping that consistent 0.0 decimal place used in the rest of the column. And even worse, look at Trial 3. 150 divided by 2 is absolutely not 7.5. It's 75. It's a massive calculation error. By using this checklist to evaluate the whole experiment, you can confidently tell the examiner that Trial 3 is anomalous and severely degrades the reliability of the entire dataset. Now, remember that graph axis trap I mentioned a minute ago? Here it is. Once a student messes up their tables, they almost always carry those exact same errors straight into their graphs. The hidden trap that destroys gradient calculations is skipping the origin without a clear break, or accidentally creating a nonlinear scale because the values were spaced inconsistently. Simply put, if your axis is broken, your gradient is broken, and your marks are totally gone. Section 3, Your Ultimate Exam Challenge. Flawed versus top band. Let's put your new framework to the ultimate test on a complex, high-mark, practical investigation question. Let's do a quick pause and predict moment. On the left, we've got your typical flawed student answer. Pressure goes up when area is small. Results look okay. It's vague, it's conversational, it's weak. Now on the right, we have a precise top band answer. Pressure is inversely proportional to area. Data point 3 is anomalous. Removing it increases reliability. The difference is literally night and day, isn't it? And this brilliantly illustrates exactly why our framework is foolproof. Look at how the top band answer perfectly maps to our 4-step data detective framework. Step 1, it stated the concept, P equals F over A. Step 2, it cited the specific data anomaly, point 3. Step 3, it gave clear scientific reasoning, inverse proportionality. And step 4, it used the exact examiner wording by stating that removing the anomaly increases reliability. That right there is exactly how you construct a full marks response on paper 6. To truly master these Cambridge exam papers, you need a psychological shift. You have to start thinking like the person grading your paper. As the examiner notes specify, a strong answer should include correct terminology, substituted values with units, and source page evidence. Don't just tell the examiner a story, prove it to them with their own data. Speak their language, use their checklists, and you are going to see a massive difference in your scores.
So you now know exactly how to analyze the data they give you, which is great. But here is a critical question you need to consider. What happens when you turn to the very last page of the exam and the question requires you to design the entire practical investigation totally from scratch, with absolutely no tables, no graphs, and no clues provided? You literally cannot walk into that exam hall without knowing how to build an experiment from the ground up. The secret is that everything we've just discussed, your concepts, your data anomalies, your scientific reasoning, and that precise examiner wording, these are the exact same linked practical and data analysis skills you need to build that final experiment. You basically just apply the framework in reverse, starting from the desired examiner wording and building the experiment backwards to generate reliable data. The ultimate difference between an average grade and a perfect score isn't just what you know, it's how you prove it. Now that you have the framework, you need to know exactly how to apply it in reverse to design a flawless experiment. The correct answer pathway to get full marks on that final, terrifying 7-mark design question is waiting for you in the very next explainer. Subscribe to our YouTube channel Ace the Exams at @aceexams_IGCSE to excel in your Cambridge examinations. Click over right now, and I'll see you there.